We've talked about the spectral domain in the context of sampling theory, and we just talked about filters. We've also talked about the Fourier transform, and in particular the fast Fourier transform used to compute the spectral centroid, which we talked about. So now we're going to continue and talk about the general process of converting from a time domain representation to a frequency domain representation where you can operate in the frequency domain, and then reconstructing the time domain signal by doing inverse transforms from the spectral domain back to the time domain. You might think from our previous discussion of filters that that's how filters work, that you take the time domain signal, go into the frequency domain, multiply by the frequency response, and then go back into the time domain. That's not actually what we do. I mean, first of all, we can't actually computationally do a Fourier transform on an infinite signal. If we tried to use short time transforms as we did with computing the spectral centroid, that could be used for filtering, but there are a lot of issues dealing with frames and windows of the fast Fourier transform, which we will talk about now. But those issues are problems in general for filtering. And it just turns out that there are time domain sample by sample processing algorithms by which you can implement all of the filters that we talked about in the previous lecture. So that's just a good thing to know. You might assume that filtering implies taking fast Fourier transforms, and that's not at all the case. Okay, but today, now we are going to talk about taking Fourier transforms of signals and operating on them. And so just to review, this is the Fourier transform in the continuous representation. This is integrating the entire signal f of t from minus infinity to plus infinity, and recall that we're computing here a real value function of frequency, and for each particular frequency we multiply the time domain signal by cosine of that at that frequency. And effectively what's going on here is we're computing the correlation between the time domain signal and that particular frequency. So this acts like a filter that, when we integrate, that pulls out the part of f of t that is represented by cosine at this frequency. And similarly, we get the imaginary part just using the sine at each frequency. The discrete Fourier transform looks just like the continuous Fourier transform, except that we replace the continuous integrals with discrete summation. We replace continuous f of t with discrete x sub I. We compute the cosine signal at discrete points indexed by I, and so on. And then recall from the discussion of the spectral centroid that in Nyquist, when we take FFTs, what comes back are arrays of floats, where the first element of the array at index 0 is the DC, or the 0 Hertz component. And then we have alternating cosine and sine terms all the way up to the top element of the array, which is the Nyquist frequency. To visualize this in a different way, here we're representing the basis functions, or these cosine and sine functions, that are multiplied by the signal. And the numbers here are the index in the array. So the 0 element of the array is formed by taking cosine of 0, which is always 1. So this is a function of all ones. We multiply this function by the input signal, the frame of samples that we're analyzing. We take the sum. So that's the zero component is just the average of all the, or the sum of all of the samples. The first element of the array, labeled 1 here, is this blue curve, which is cosine. It's a single period of cosine across the duration of the analysis frame. The next element in the array is the sine term, so it's a single sine function over the length of the array. And proceeding from there, we have 2 cycles of cosine, 2 cycles of sine, then 3 cycles of cosine, 3 cycles of sine. And each one of these is multiplied by the input samples. You form the sum and stick that in the array. And finally, the Nyquist term illustrated down here has n over 2 cycles of a cosine. So we're just alternately multiplying the samples by +1, -1, +1, -1. Frequencies represented by these elements of the array are shown by k over duration, so for index k from 0 to n over 2.